I'm Madeleine Abernot from the LIRM laboratory in Montpellier in France. And today I'm going to present some work we have done on using oscillatory neural network as heteroassociative memory for image edge detection. And so this is a work done in the framework of the Neuron project, so European project called Neuron. So I'm going to start by presenting a little bit oscillatory neural networks, the paradigm, and how we use it as a heterogeneous associative memory. And then I'm going to show how we use this ONN-HAM architecture to perform some edge detection applications. So first, oscillatory neural networks. So ONNs are networks of coupled oscillators. So it's an analog-based computing paradigm where each neuron is emulated with an analog oscillator, and we couple the oscillators with analog components like resistors or capacitors. And so in the Neuron project, we consider only phase computation. So the oscillators have a fixed frequency, and we represent the information in the phase relationship between the oscillators. And so using this phase computation with fully coupled networks, so recurrent fully coupled networks with oscillators, it is shown in the literature that it can work as auto-associative memory, like the Hopfield neural networks. So it means that we can learn some patterns using some unsupervised learning rules like Hebbian, Storky, or others. And so when we learn the patterns, we represent the learning pattern in the weights between the neurons. And so if we input a corrupted pattern, so if we consider images a pattern with 30 pixels, the network will evolve and stabilize to the learning patterns. And so in the Neuron project, we are trying to explore other architectures and other applications. And that's why in this work, we explored can we use ONN as heterogeneous associative memory. So instead of associating a fuzzy pattern with the clear pattern, we would like to associate an input with an output. And so using some input layers connected with output layers. So like this, we have different dimensions. We reduce the number of synapses because a fully coupled network uses a lot of synapses as well. And so using this in-out functionalities, we looked into can we perform some edge detection applications. So just a small part on how edge detection algorithms are performed usually. So the state of the art is using some convolutional filters that scan the image. So the idea is that you take a small part of the image and you apply a convolutional filter with some coefficients to detect if there is an edge or not. So the two main algorithms are Sobel and Canny algorithms. They both use convolutional filters. For example, the convolutional filters of the Sobel algorithm are those two kernels with those coefficients. So one is more to detect a vertical edge and the other one to detect horizontal edge. And so combining the two and applying the two convolutional filters in the full image, they are able to retrieve the edges of the image. And in addition, the Canny algorithms adds a Gaussian filter to smooth first the image and then apply the convolutional filters, because using only convolutional filters is really sensitive to noise. So we have tried during this work to replace the two convolutional filters with one ONN as a heteroassociative memory. So the idea is to have as input the small part of the image we want to detect an edge in, and we consider this as the input of the network, and we would like to have the output saying if there is an edge or not inside the image. So what we have performed to configure this neural network is we use the coefficients of the Sobel kernels we have seen before, and we also associate the Sobel kernel representing the vertical edge with a pattern, and the Sobel kernel with representing the horizontal edge with another pattern. So if you look here, we have -1, -1, and +1, +1, but it means that, for example, -1 is an oscillator with a 0-degree phase, and a +1 is an oscillator with a 180-degree phase. And so the idea is if we find this pattern at the output of the neuron, is we have an edge associated with a vertical edge And if we find this pattern, we have an edge associated with an horizontal edge. And in case we retrieve none of them, it means we don't have detected any edge in this small part of the image. So in this work, we have tested different systems. First, we have made some tests with using a MATLAB emulator with an HNN, so considering neurons as pins and a sign activation function. And then we have done some additional tests using a digital ONN design. So if you want more details, there is a paper about this design. But the idea is that we use, instead of using analog oscillators, we use digital oscillators, so between 0 and 1, and we have this phase computation between the oscillators. So looking at the results now, we did first some evaluations on grayscale maps, so to see how the edge detection filter works on different grayscales. And so what we have seen is that our MATLAB emulator and the digital ONN can retrieve the edges up to this 6th level of gray, like the Kani algorithm, if we compare with the others. And in comparison, the Sobel algorithm cannot go as far in the gray level, let's say, as our algorithms. However, we have also seen that the digital ONN, when we go too far in the gray scales, have also unstable states. So it means that if we input a pattern, the output will always move in time, and we cannot determine which output it is represented clearly. And the last thing that we would like to highlight is about the number of edges we detect, because we can see that the lines are a little bit larger when considering our MATLAB emulator and the digital ONN more on the black and white contrast. And this is because we detect twice each edge. So in this algorithm, we detect on both sides of the edge. This is why we have like twice detected edges. So then we move to see how it behaves on more realistic images. So not only vertical, horizontal, but also diagonal and round shapes. And what we've seen, so we have tried using some MNIST images representing handwritten digits. So first with black and white and then with grayscale images. And so we retrieve approximately the same behavior as before. So we detect twice each edge, and however, we see that, for example, this left diagonal is not retrieved, but with the state-of-the-art normally it is correctly retrieved. And we also see that the Sobel, for example, can have trouble to differentiate two edge. And on the grayscale parts, so what we see is we detect also a lot of edge, and we almost redo the first image, so the starting image. And this is because we detect really well the grayscale's contrast. So we detect an edge approximately everywhere in the image. And this is a problem, for example, if we treat grayscale images, but also noisy image, because we will detect all the noise as an edge, but it's not an edge. And so this, we should maybe include, as the Kani algorithm, a first layer to remove the noise and then apply our algorithm, edge detection algorithm. So then here is just a larger view on how it works on large scale image. And what we see is that the Sobel and Kani have thinner lines, and we have larger lines. So we detect still twice, but we have approximately the same precision as the other algorithms. So to finish, I'm going to show a little bit the performances. So considering the digital ONN and how we perform simulation, we consider a target FPGA as this one. And so what we have reported as results in terms of initialization and computation time. So for only one single ONN performing on a small part of the image, so we have a computation time between 1 and 2 microseconds depending on the image, because it can vary, and the initialization is still the same. But so to compute one ONN, we need approximately 2 microseconds. And what is also important to note is that the number of resources inside the FPGA that is taken by the ONN is really small. And this is important because we made some estimations on how long it will take to process the full image with our ONN sequentially. So considering a computation time of approximately 2 microseconds. And what we have seen is that it grows really fast with the number of pixels in the image. And if we consider like real-time image processing, like a standard camera of 30 images per second, we can only treat images of up to 120 by 120 pixels. So it's quite a big limitation. And because the other state of the art, they do not say go faster than this. And so in order to improve this, the fact that our ONNs takes really low amount of resources, the idea is to use multiple ONNs in parallel to scan the image. And so we made some estimations using 20 ONNs in parallel. And we can, in this case, scan a 500 by 500 pixel image in real time. And also the FPGA we consider has a maximum operating frequency of 175 megahertz. And so we could also consider to use more powerful FPGA to have a higher frequency and so a higher, a faster time, computation time. So thank you, and I'm open for questions.